Hi, this is M. Sriram from CSC D section. Topic is Advances in Polymer Integrated Optics. Polymer. The attractive forces between polymer chains play a large part of determining the polymer's properties. Because polymer chains are so long, they have many such interchain interactions per molecule, amplifying the effect of these interactions on the polymer properties in comparisons to attractions between conventional molecules. Different side groups on the polymer called lend the polymer to ion bonding or hydrogen bonding between its own chains. These are stronger forces typically result in higher tensile strength and higher crystalline melting points. A polymer may part is a substance or material consisting of very large molecules or macromolecules composed of many repeating subunits due to their broad spectrum of properties. Both synthetic and natural polymers play essential and ubiquitous roles in everyday life. Polymers range from familiar such as polystyrene to natural biopolymers such as DNA and proteins that are fundamental to biological structure and function. Polymers, both natural and synthetic, are created via polymerization of many small molecules known as monomers. Their consequently large molecular mass relative to small molecule compounds produces unique physical properties including toughness, high elasticity, viscoelasticity, and a tendency to form amorphous and semi-crystalline structure rather than crystals. This is the structure of polymer. Properties. Mechanical properties. A polyethylene sample that has nicked under tension. The bulk properties of a polymer are those most often to end use interest. These are properties that indicate how the polymer actually behaves on a microscopic scale. Tensile strength. The tensile strength of a material quantifies how much elongating stress the material will endure before failure. This is very important in applications that rely upon strength will hold a greater weight before snapping. In general, tensile strength increases with polymer chain length and cross-linking of polymer chains. Young's modulus of elasticity. Young's modulus quantifies the elasticity of the polymer. It is defined for small strains as the ratio of rate of change of stress is strain like tensile strength. This is highly re- relevant in polymer application involving the physical properties of polymers such as rubber bands. The modulus is strongly dependent on temperature. Viscoelasticity describes a complex time dependent elastic response which will exhibit stresses in stress strain curve when the load is removed. Dynamic mechanical analysis or DMA measures this complex modulus by oscillating the load and measuring the resulting strain as a function of time. Chemical properties. The attractive forces between polymer chains play a large part in determining the polymer's properties because polymer chains are so long. They have many such interchain interactions per molecule. Comparison to attractions between conventional molecules. Different side groups on the polymer can lend the polymer to ionic bond and hydrogen bonding between its two chains. These stronger forces typically result in higher tensile strength and higher crystalline melting points. The intermolecular forces in polymers can be affected by diplomas in the monomer units. Polymers containing amide and carbonyl groups can form hydrogen bonds between adjacent chains. The partially positively charged hydrogen atoms in NH groups of one chain are strongly attracted to the partially negatively charged oxygen atom C double bond O. The high tensile strength or melting point of polymers containing urethane and urea linkages. Polyesters have diplo-diplo bonding between the oxygen atoms in C double bond O groups and the hydrogen bonding between the oxygen atom O C double bond O bonding, so a polyester's melting point and strength are lower than Kelvar's Twarnon. The polyesters have greater flexibility. Polymers with non-polar units such as polythene interact only through weak van der Waals. As a result, they typically have lower melting temperatures than other polymers. Structure of polymerization. Polymers have been essential components of commodities since the early days of humankind. The use of wool, keratin, cotton, and linen fibers, cellulose for garments, paper, red cellulose for paper are just a few examples. Obtain artifacts. The latex sap of reached Europe in the 16th century from South America. Long after the Olympic Maya and Aztec had started using it is a material to make balls, waterproof textiles and containers. The chemical manipulation of polymers dates back to the 19th century. At the time, the nature of these species was not understood. The behavior of polymers was initially rationalized, considered them as colloidal aggregates of small modules held together by unknown forces. Not Notwithstanding the lack of theoretical knowledge, the potential of polymers to provide innovative, accessible, and cheap materials was immediately grasped. The work carried out by Bracken and Parks Ludersford headed and many others on the modification of natural polymers determined many significant advances in the field. Their contributions led to the discovery of materials such as galalith, parkisin, rayon, vulcanized rubber, and manufacturing process and reached households as garments components. Example fabrics, buttons, crockery, and decorative items. In 1920, Hermann Stonger publishes his seminal work Uber Polymerization, in which he, pro- he proposed that polymers were in fact long chains of atoms linked by covalent bonds. His work was debated at length, but eventually it was accepted by the scientific community. Because of this work, Stanger was awarded the Nobel Prize in 1953. After the 1930s, polymers entered a golden age during which new types were discovered and quickly given commercial applications. Replacing was fueled, fueled by an industrial sector with a strong economical drive, and it was supported by a wide academic community that contributed with innovative synthesis of monomers from cheaper raw materials. More efficient polymerization process, improved techniques for polymer characterization, and advanced theoretical understanding of polymers. Synthesis. Main article Polymerization, a classification of the polymerization reactions. Polymerization is the process of combining many small molecules known as monomers into a covalent bonded chain or network. During the polymerization process, some chemical groups may polyester the monomers are terephthalic acid COOH, C6H4 COOH, and ethylene glycol OH CH bond CH2 bond CH2 bond OH, but the repeating units is CO bond C6H4 bond C double bond O C COO bond CH2 bond CH2 bond O, which corresponds to the combination of two monomers with the loss of two water molecules. The distinct piece of each monomer that is incorporated into the polymer is known as repeat unit or monomer residue. Synthetic methods are generally divided into two categories: step growth polymerization and chain polymerization. The essential difference between the two is that in chain polymerization, monomers are added to the chain one at time only, such as in polystyrene, whereas in step growth polymerization, chains of monomers may combine with one another directly, such as in polyester. Step growth polymerization can be divided into polycondensation, in which low molar mass byproduct is formed in every reaction step, and Polyaddition. Polymer architecture. Main article: Polymer architecture. Branch point in a polymer. An important microstructural feature of a polymer is its architecture and shape, which relates to the way branch points lead to deviation from a simple linear chain. A branched polymer molecule is composed of a main chain with one or more subsequent side chains or branches. Types of branched polymers include star polymers, comb polymers, polymer brushes, dendronized polymers, ladder polymers, and dendrimers. There, there exists also two-dimensional polymers, which are composed to topologically planar repeat units. A polymer's architecture affects many of its physical properties, including solution viscosity, melt viscosity, solubility in various solvents, glass transition, temperature, and the size. Techniques may be employed for the synthesis of a polymer material with a range of architectures. For example, leaving polymerization. Linear polymers with periodic structure, low branching, and stereoregularity. Example: non-atic have a semi-crystalline structure in the solid state. In simple polymers such as polythene, the chains are present in the crystal in zigzag conformation. Several zigzag conformations form dense chain packs called crystallites or lamellae. The the lamellae are much thinner than the polymers are long, often about 10 nm. They are formed by more or less regular folding of one or more molecular chains. Amorphous structures exist between the lamellae. Individual structure exist between the lead to entanglements between the lamellae and can also be involved in the information of two or more chains that called tie molecules several. Thank you for watching my video. Have a nice day.